thanks very much for having me here. And I will be speaking today about some work that we've been doing on blue waters for the past 2 to 3 years now. The work has been done primarily by my students. Not sure what happened there. Okay. Hui Li, who is now was a PhD student with me, now a postdoc at Yale, and Andrew Huang, a master's student with me, who's now working at the Naval Research Laboratory. So working with HPC systems and being good at programming can help you get good jobs, that's for sure. And I want to mention the NCSA team that we've been collaborating with, David Bach, who's a lead visualization programmer, Ryan Mokos from Blue Waters, who's a senior research programmer, and also Rob Cisneros, who works in the data analytics and visualization group. This has been a very kind of productive and fruitful collaboration over the last couple of years, and these various agencies have really kind of helped to make that happen. So why do we care about tropical cyclones and climate? First and foremost, tropical cyclones pose serious risks. Here's a couple of recent examples. Katrina from 2005, Hurricane Harvey from 2017. These two storms are now tied as the costliest hurricanes on record, $125 billion each in 2017 dollars. And you can see the damages that are brought on by these systems. These pose major environmental hazards. But in addition, when you combine that with failures of critical infrastructure, you can lead to really devastating consequences, as shown here through the extensive flooding here shown in the aftermath of both Katrina and Harvey. And then, of course, events like this then lead to salacious or contentious news reports, such as these are 2 Time magazine covers that came out of each of these events, suggesting some link between hurricanes and climate. You know, are we making hurricanes worse, or the storms keep getting stronger? So understanding these connections, or understanding the connections between tropical cyclones is really quite critical for coastal planning, flood risk assessments, future projections. So will tropical cyclones change in the future? This is kind of the million-dollar question, but it's a very difficult question to answer using global models anyway, the type of global climate models that we use to make projections of the future, because a lot of these models suffer from coarse resolution, or they're not fine enough scale to simulate tropical cyclone circulations, and they also lack ocean-atmosphere coupling. Here's a couple of recent examples, kind of high-profile examples from Carrie Emanuel 2013, who uses a very nice downscaling technique to take low-resolution climate model outputs and determine what are the tropical cyclone climatologies, what should they look like based on these large-scale environmental factors. And he shows that from these downscaled products, we find a potential increase in tropical cyclone activity in the future under global warming. We can also now directly simulate these events by going to fine enough scales. Here's some results from some GFDL models, some recent models at like 50-kilometer horizontal resolution, 25 kilometers are able to capture tropical cyclones, simulate them directly. But these are very expensive to run, computationally expensive, and also they typically don't include a dynamic ocean. The ocean is considered a fixed boundary condition, again, due to the computational expense and just the sheer magnitude of running these models. But what we found is that the ocean is actually quite important for tropical cyclones. Tropical cyclones derive their energy from the ocean. So how can we really understand how they're changing with climate, or how climate's going to change them, if we don't include these interactions? And here's a simple cartoon of this, showing how tropical cyclones can affect their environment, or more specifically the upper ocean. This is a simulated track of a hurricane passing along the eastern seaboard of the United States. This is Hurricane Gert in 1999, and you can see it leaves a cold wake behind it. It cools the ocean surface. This cooling comes from 2 major factors, one of which is enthalpy fluxes, or the evaporation of water to the atmosphere, which helps fuel the storm, removes heat from the upper ocean. But a more important mechanism is vertical mixing. These storms have extreme winds that tend to mix the upper ocean, and the upper ocean is stably stratified with warm water on top of cold water. So as you mix this water, you're mixing cold water to the surface and mixing warm water down into the ocean interior. And we see this here in this simulation, a pre-storm and post-storm temperature, vertical temperature profile, showing a cooling of the surface ocean and a deepening of the mixed layer. So you're reducing the overall temperature of the upper ocean, but you're also mixing heat downward. And if we take the difference between the post-storm minus pre-storm temperature profiles, this is exactly what we see. We see cooling at the surface, warming in the interior. So this process introduces multiple feedbacks on or two different feedbacks on multiple scales that can have climate implications. First off, you have a short-term negative feedback. As you cool the surface ocean, this is going to limit storm intensification because you're limiting the amount of energy that's available for the storm to develop and intensify. And this is particularly important for slow-moving or large storms that have a large aspect ratio. And this works on days to weeks. It can also cool if I cool the ocean surface here and then another storm passes through the same region, it will most likely be less intense than it would have been prior to the previous storm. So this is a short-term negative feedback, works on days to weeks, but there's also a long-term positive feedback due to the injection of heat into the interior ocean. This additional surface warming provides additional energy for future storms, kind of working on months to years. So you consider this as an irreversible mixing, irreversible heat convergence in the tropics. You're warming, or you're injecting heat into the subsurface ocean, which then can be advected away by large-scale currents or something, but it's an irreversible mixing or heating of the ocean. And if we expand this out to global scales, what we find is that this mixing actually matters for global energy budgets, global mixing budgets for the ocean. So this is an annually averaged kind of summation of all the cold wakes associated with storms. And what we've done then is convert that, this is based on observations, convert this into a diffusivity representation of vertical ocean mixing. So how much mixing do you need to achieve this type of cooling on a year-to-year basis? And it turns out that this type of mixing is what is typically parameterized, or this level of mixing is what's typically parameterized in global models as subscale mixing processes that aren't captured. So the point here is that these kind of transient extreme weather events may significantly contribute to ocean mixing budgets, which are currently parameterized in ocean models. Even more interestingly, if I do a regression between SST and mixing, what we find is a very positive relationship between tropical cyclone mixing and SST. And this fits with kind of budget scale analysis, diffusion analysis of global energy budgets for the ocean, meaning that as you have a warmer temperature, warmer ocean, in steady state, you have to mix more you have to diffuse more heat into the interior. But this is a little bit counterintuitive, because if you think about a warmer surface ocean, this typically is represented or associated with stronger stratification. Stronger stratification will inhibit mixing. So this is a little bit of a paradox, but what it suggests is that under warmer conditions, you can actually experience more mixing because you have more storms. So the storms actually provide potentially more storms. The storms provide a physical mechanism kind of linking this energy budget analysis. Okay, so that's kind of the background problem. I'll go very briefly kind of through what we've been doing. We've been using CESM, which is a numerical deterministic climate model that simulates physics, dynamics, and interactions between the atmosphere, ocean, land surface, and glaciers. We're using 25-kilometer resolution atmosphere, coupled and uncoupled to a 1-degree ocean. And we use CESM because it scales pretty well on blue waters. We scale it out to about 15,000 cores. We're adapting the model from other CESM projects, such as led by Susan Bates at NCAR and Don Webbles at the University of Illinois. They've done a lot of the heavy lifting of porting the model there, tuning it and such. And we're kind of piggybacking on some of that early work. We're using the high resolution model. We're running 3 multi-decadal simulations beginning with a coupled pre-industrial control, which generates tropical cyclones kind of organically within the model. We're then using these boundary conditions from the coupled control, or the outputs from the coupled control as boundary conditions to atmosphere and ocean-only simulations. So the atmosphere-only simulation is using ocean boundary conditions from the coupled run, which allows us to isolate the effect of coupling on simulated tropical cyclone climatologies. And then we're also running an ocean-only simulation with the atmosphere boundary conditions from the coupled simulation, which allows us to isolate the effect of tropical cyclones on the upper ocean. So what the main idea here is that we've got a coupled model that just simulates tropical cyclones spontaneously. We use that as our control, and then run ocean-only, atmosphere-only runs with the boundary conditions from the coupled simulations, which allows us to cut the feedbacks from the coupled model and isolate the effects of these tropical cyclones. Okay. Some of the major challenges that are associated with it, this was a huge undertaking by Hui Li in particular. It took her several years to kind of run all of this and work out all the details, but some of the major challenges are the fine spatial resolutions that are necessary to run these simulations. We're running 25 kilometer atmosphere coupled to a dynamic nominal 1 degree ocean. This is really at the cutting edge of climate modeling, Earth system modeling. Coupling the ocean and the atmosphere, scale mismatches, this is always an issue. Here's an example of this. This is what a tropical cyclone looks like in the 25 kilometer atmosphere. This is what that same cyclone looks like to the ocean when you're dealing with a 3 degree ocean, 1 degree ocean, 1/10 of a degree ocean. Right? So even though you're getting something in the atmosphere, it doesn't necessarily mean that it's translating the impacts to the ocean. This is what the ocean sees. The integration lengths, we're trying to run multi-decadal simulations. We've run a couple hundred years kind of total right now between all the simulations, but we're analyzing weather statistics in a climate model. So we're looking at extremely high frequency I/O, input-output, sub-daily model outputs, including the full ocean, because we want to understand what the response of the ocean is on transient or kind of weather timescales. And then, of course, post-processing and analyzing, visualizing the results. When you're dealing with these huge simulations with hundreds of terabytes of output, you know, how do you wrap your head around it? How do you analyze it? How do you make sense of it? First and foremost, how do you even find the tropical cyclones? These are all major challenges. And so Blue Waters really provides the unique capabilities to overcome these challenges, including the big scalability. We're able to scale the model out to 15,000 cores. Large allocation sizes. We would only be able to do a small fraction of what we do on Blue Waters using other systems. And also the fantastic researchers and support team that we've been collaborating with. Okay, a couple of quick recent results. Some of these are newly published. We'll just look at kind of differences between the global model, coupled and uncoupled model. This is what tropical cyclones look like in the fully coupled model. This is the atmosphere-only model. We find that the model captures key elements of, whoops, I keep doing that. Model can simulate realistic spatial patterns. It captures the annual cycle for different basins. This is a plot of the number of tropical cyclones as a function of month for each of the key tropical cyclone basins. So while you see some differences between the model and observations, or even between the models themselves, we find that the model can generally reproduce reality, which is a good first step. We also find some strong sensitivities in the model as well when you go from coupled to uncoupled, or uncoupled to coupled, either way. Generally, the tropical cyclones are stronger in the atmosphere-only simulation than in the coupled model. I highlight this here in these histograms, or the box whisker plots here, showing red here is our coupled model, green is our atmosphere-only simulation. Globally, we tend to get more on average events for both weak storms and strong storms. In terms of an intensity distribution, we get stronger maximum wind speeds in the atmosphere-only model versus the coupled model. And we find that the differences in these tropical cyclone characteristics are directly linked to the missing ocean atmosphere feedbacks in the uncoupled model. shown here as a regression between SST and the maximum wind speed, showing that maximum wind speeds tend to happen at larger SSTs than the atmosphere-only model versus the coupled model. So how do the interactions, or how do these ocean-atmosphere feedbacks manifest themselves, or how do they affect tropical cyclones themselves in the model? We can find this by moving now to a Lagrangian sense, where we look at how does surface temperature respond in the tropical cyclone frame of reference. This is shown here in this atmosphere only, or in these two plots here, the time series plots, atmosphere only on the left, coupled on the right, showing blue is the surface temperature, red is the surface wind, and green is the surface fluxes, showing that here's where you reach peak intensity. This is kind of on a composite storm by storm basis, so this is including all storms globally, the relationship between intensity and sea surface temperature directly under the storm. What we find is that the tropical cyclone intensity peaks along with surface fluxes, but the SST does not respond, right? So the SST is fixed throughout. It's a fixed boundary condition. Whereas in the coupled model, the SST response now is quite large. You get cooling as the tropical storm reaches its maximum intensity. The intensity that it reaches is smaller than in the atmosphere-only simulation, and the surface fluxes are also smaller. So the point of this work, or the point of this result here, is that these interactions can modulate tropical cyclone intensity, evolution, activity, and the models with these fixed ocean conditions are missing these feedbacks, which is important if we're going to try to understand how they fit within the larger scope of climate change. I'll end this talk with a nice animation that David Bach and Rob Cisneros worked with us to produce, looking at how can we visualize some of these interactions, how do we visualize weather interactions between the atmosphere and the ocean in a global climate model, as well as the interactions with the different climate processes on multiple scales. So how do you go from a weather scale to a climate scale in terms of an animation product? Let's see if I can get this to work. So this is a nice animation that was put together. It's relatively long, so I'll kind of scoot through this if I can. Maybe I can't. I guess I can't fast forward this. All right, well, maybe I'll skip that one then for now. All right, I'll skip the animation for now. I think Susan Bates will be showing this animation tomorrow morning in the plenary session as well. So I'll just briefly describe the next steps. The final steps we're doing with this project is a 4-time CO2 simulation where we're running the fully coupled model under increased carbon dioxide scenarios. These are currently running on blue waters. And the main thing is how are the tropical cyclones going to change to this new extreme environment, where again, we don't have to rely on any sort of statistical proxies or downscale or anything. We're dealing with a high resolution model that directly simulates these events. So some conclusions: we conducted a series of sensitivity experiments highlighting the importance of ocean-atmosphere interactions for tropical cyclones. The coupling significantly influences tropical cyclone activity with important climate implications. And these results point to the importance of these interactions when considering tropical cyclones and climate change. It also paves the way for new coupled modeling approaches now that we have systems such as blue waters and the next exascale systems, where we can really look at these coupled processes with much more fidelity. And I'll just leave you with a few of the products that have come out of this project. Thank you.